And concavity is how a function is bending. Now, here is the official definition of concave up. It's concave up if it is above all of its tangents. Now, that is not an easy visual. I think concave up is easier to see as like a smiley face. Things are looking up. You're happy. And the reason we have that is saying that the curve lies above its tangents. If I draw a bunch of tangents on here, can you see that they would all be below the curve? And that's what that definition is saying. But as far as remembering what concave up looks like, think of a smile. There we go, add the eyes. Because that is concave up. Similarly, so here is, well, before we get to concave down, here is a bunch of curves that are concave up. So when we're looking at something that's concave up, what's happening to the derivatives? Okay, here are my tangents in each of these graphs. In each of these graphs, I've also listed the derivative and said what the slope of that line is. For something to be concave up, you will notice that our derivatives, I go from 0.24 to 1.07 to 4.05. My tangents are increasing in their slope. Can you see how the slopes are going from a small number to a big number? For this parabola that's concave up, if we look from left to right, my tangent on the far left has a negative slope. Here I have a slope of 0, and here I have a slope that's positive. If my slopes are increasing from left to right, what that means is my second derivative is greater than 0. And anytime your second derivative is greater than 0, your function will be concave up. Again, we're going to do something similar to what we did with the first derivative, where we showed increasing and decreasing, where we checked if it's positive or negative. We're going to do something with the second derivative to find out if it's concave up or concave down. And similarly, if your tangents decrease, then it's going to be concave down. But again, to remember the shape of what concave down is, you can think of a sad face. And anything that's sad is concave down. And again, now what's happening is your derivatives are decreasing. So if we look at this parabola, our derivative started at a positive number, moved to 0, and then keeps getting more and more negative. So here we have a function, and I have labeled the blue parts where things are concave up, and the red parts where things are concave down. So if we wanted to write the intervals where it's concave up, we could say, well, it's concave up from -4 to 1, and then from 3 to 6, and then again from 6 to 8. We use round brackets here because those values on the end where it changes concavity, we're going to call those points of inflection. And at that point, the function is neither concave up or concave down. And it's concave down from 1 to 3 and from 8 to 9. P, Q, and R, those are called points of inflection, where things change concavity. There's a special name for the point at 6. Can't remember it right now, so I'm going to just call it a pointy point or something. Can you see at that pointy point that there's so many different tangents that could balance on that point? So the derivative doesn't exist at that point. It would be undefined at that point. So a point on a graph is an inflection point if the second derivative is equal to 0 and the second derivative changes sign. So what we're going to find on this one, later on we're going to have a number line for our second derivative. And we would put point P, point Q, 6, which would be a non-permissible value, most likely, and R, all on that function. And you would plug values in and find out that some sections are positive, those are concave up. Some sections are negative, those are concave down. So later on, we're going to find out that if at a point you change from concave up to concave down, what happens at that point is the second derivative is equal to 0 and your second derivative is changing sign. And at an inflection point, we're also going to find that the first derivative doesn't change sign. So inflection points is where it changes concavity, and then you have a special inflection point called the stationary point of inflection if it changes concavity and the first derivative is equal to 0. So you have a stationary point of inflection. The first derivative is equal to 0. The second derivative is equal to 0 at that same point. An example of this is your x cubed graph. Right here at 0, 0, if we did the derivative of x cubed, can you see this is the x cubed graph? Your derivative is 3x squared. And so you get a stationary point at x equals 0. Because our derivative is equal to 0. But if you plugged values in to see if it's increasing or decreasing, you would find out what happens when I plug in something less than 0. It's positive. So our original graph is increasing, which is true, right? From left to right, it increases up to 0. What happens after 0? If I plug in something positive into 3x squared, it's still positive. It's still increasing. When I do the second derivative, 3x squared, the derivative of that would be 6x. It's still equal to 0 when x is equal to 0. And so we have an inflection point. But if I look at what happens on my number line at 0 with my second derivative, what happens when I plug in a value less than 0 into my second derivative? It's negative. That means it's going to be concave down. And when I plug a value larger than 0 into my second derivative, it's positive, meaning that it's going to be concave up. That's a stationary point of inflection. A non-stationary point of inflection just means that your first derivative is not equal to 0, but your second derivative is equal to 0, and your function changes concavity at that point. Part 2 of this says the gradient on either side of your point have the same side. So here I'm going to do a point, and I'm going to have concave up before that point and concave down after that point. So maybe it's some sort of x cubed graph, or maybe it's a sinusoidal. But what they're trying to say is, what is the slope of the tangent on this side? Positive or negative? Positive. And on this side? Still positive. So the gradient of the curve, or the slope of the curve, on either side of this point still have the same sign. Then you know that they're both positive or both negative, but it changes concavity at that point. That will be an inflection point that's non-stationary. So it's important to note here that if we want to show that something is an inflection point, it's not good enough just to show the second derivative is equal to 0. That's a key starting point, but it's not enough to just do that. You also have to show that either the first derivative does not change sign at that point, or that the second derivative changes sign from positive to negative. We'll leave our examples, well, let's do just this one quick, and then we'll leave the rest of the examples for next time. So, if you take y equals x to the 4, and we do the derivative, 4x cubed, and we do the second derivative, 12x squared, we find out that your second derivative is equal to 0 when x is equal to 0. Doing our first derivative test and putting 0 in there, we see that it is decreasing before it's equal to 0 and increasing after. So our first derivative is changing sign at that point. It's going from negative to positive. That makes that point a local minimum, but it will not be an inflection point.